Hello, welcome to today's Zoom in. It is my great pleasure to have Andrés Meléndez here today, who will be speaking about fixed polytopes of the permutahedron.
Awesome. Thank you so much for joining the seminar today. Yeah, so this is joint work with Federico Ardila at SFSU, Anna Schindler at North Seattle College, and Mariel Supina at UC Berkeley. So it's kind of one overall big picture, but two separate projects, one building off the other. And so I want to start. I don't know what people's background are in the rooms, but I'm just going to try to define everything as much as possible. I won't assume people know what a polytope is, for example. So what are our main characters? Our main characters are polytopes. And I believe that everybody at least has seen polytopes in the past, even though you might not know the definition. But a convex polytope is the convex hull of finitely many points in Rn. So we call a polytope, and so you can think of the convex hull kind of, I think what people tend to say is in 2 dimensions, if you had little nails or something and you have a rubber band around it and let it snap, that gives you the convex hull. In 3 dimensions, you might want to throw your points up into 3 space and then saran wrap them, and then it gives you, flat sides, and the shape that you get after saran wrapping it is the convex hull. And so we say a polytope is integral if all its vertices have integer coordinates. And similarly, we say it's rational if its vertices have rational coordinates. And so we're going to think eventually of these polytopes as being on the integer lattice. So we're placing the polytope somewhere on the integer lattice or translating it on the integer lattice. We're also going to care about dilating these polytopes. And so for an integer dilation, and so we're going to say that TP is the teeth dilation of P, okay? And as I said earlier, I'm convinced you've seen polytopes because you probably have heard of the Platonic solids. And so the Platonic solids are 3-dimensional polytopes. And so you can think of polytopes as higher dimensional generalizations of polygons or polyhedron. And so one notion that we will need is how do you sum 2 polytopes? And so we say, or more polytopes. And so we say that the Minkowski sum of K polytopes is done integer, is coordinate-wise with points in each of the polytopes. And so maybe an example is probably more illustrative. So let's consider just the square and the triangle. And so you can kind of think of grabbing one of the other polytopes and kind of sliding it everywhere. So if I grab this, you can see my cursor, right? If I'm, okay. And if I grab this triangle and I'm kind of just sliding it through all the points on the square, this is the polytope that I get at the end. Yeah, so it's all the summing all points in the corresponding polytopes. Okay. And so a special class of Minkowski sums are what we call zonotopes. And so a zonotope is a polytope that can be expressed as some translate of a Minkowski sum of line segments. Okay, so it's using this definition, but the polytopes that we care about are just line segments. So can we realize the polytopes as line segments? And so I told you that we care about polytopes on the integer lattice. And so maybe we'll start with a small example to kind of give us an idea. And so some of you might be familiar with Pick's theorem, and if you are, you'll see what its use is good for. So here's just a small example. Let's just consider this triangle T, yeah. And so I want to compute the continuous discretely. So that's maybe one theme in this kind of work. So what do we care about? Well, we care about maybe in this case area. So can we compute the area just by counting, yeah? And so Pick's theorem actually allows us to do that. And so for a lattice polygon containing I interior points, B boundary lattice points, Pick's theorem from 1899 tells us how to compute the area. And so that's the area is equal to the number of interior lattice points plus half the boundary points minus 1, right? And so I mean, this is half a unit square, so we know that the area here is 1/2, right? But if we compute it just using the points, we see that how many interior points it has. It has none, right? It has 3/2 when I substitute the 3 of the boundary points here, -1, which gives us again the half. Yeah. And so equivalently, I care about the enumerating the number of lattice points. And so the number of lattice points for a polygon is given by its area plus half the boundary points plus 1. Okay. And so I don't know if you've seen this before, but it's a kind of nice result because it ties in something that is continuous with something very discrete, because we just have to number or enumerate the lattice points. And so a question can be, well, does this hold for higher dimensional polytopes? And the sad story is that it doesn't, in a sense, and that is a counterexample to Pick's theorem in higher dimensions is given by John Reeves, where you're thinking of this Reeves tetrahedron. And I should have put a picture in it, and I didn't. But the Reeves tetrahedron is just thinking about if you're taking the simplex that just falls where you have just a triangular face on the unit square in 3 dimensions. So here's 3 dimensions. If I just take the simplex here and some point higher up here, right? It's always going to be smaller. Its volume will always be contained in this like rectangular thing. And so when you start thinking about enumerating the lattice points and you kind of move the point on the top of the simplex, you'll change its volume, right? But the number of lattice points stays the same. And so it breaks Pick's theorem in higher dimension. But in a way to think, to resolve this, we can think about dilations of the polytope. And so here we're gonna dilate the triangle by integral dilations. And so here I have 2t, 3t, and 4t, right? But it continues on and on. And so so the question is, can we enumerate the lattice points and the dilations of these polytopes? And the answer is yes, right? We can count them and we can try to see if there's some counting function. It turns out that in this case, the counting function for L sub t, and sorry, I should have said L sub t is what I'm gonna call the counting function. So the lattice point enumerator. And it's given by 1/2 t squared plus 3/2 t plus 1. This should kind of look like Pick's theorem, right? Because again, it's only in 2 dimensions, right? And if I enumerate just the interior of the interior lattice points, that's what this L sub t circ means, I also get some polynomial. So the question is that always true? Do I always get a polynomial to enumerate the lattice points in the dilations of the polytope? And the answer is yes. And that's a result from the 1960s by Eugene Ehrhart, who's a French mathematician who didn't get his PhD until the age of 60. He was a high school teacher and did most of his work as a high school teacher. So more of the story for any grad students who might be listening is it's never too late to finish your PhD. And so I always like to share that story because it's, I think, a little bit inspiring. And so if we have now a lattice polytope, the lattice point enumerator is actually polynomial in degree d, where d is the dimension of the polytope, okay? And so what do we call that polynomial? Well, we call it the Ehrhart polynomial, okay? And as is a common theme in combinatorics, we like to encode these things in generating polynomial or generating series. And so we're gonna encode the lattice point enumerator in a series, which we call the Ehrhart series, okay? And so the Ehrhart series is of this form. It has this rational form where we call the numerator the H star polynomial, okay? And for lattice polytopes, this is kind of like, well, this is a change of basis, right? But the coefficients of the H star polynomial, if you sum up the coefficients of the H star polynomial, you get the volume for the polytope in the lattice polytope case, okay? So, and you can see that from the Ehrhart series, we can write this lattice point enumerator kind of in this polynomial basis, okay? And so a question is, you know, as combinatorialists, we care about counting, right? And when we have some generating polynomials, do these coefficients of the polynomials count anything? And so the answer is yes. So what do we know about these coefficients? Well, the leading coefficient of the Ehrhart polynomial is always the relative volume, okay? And if it's a full dimensional polytope, this is actually the Euclidean volume, okay? And but I write relative volume because you can have maybe a two-dimensional polytope living in 3 space, for example, okay? Then we know that the second coefficient is half of the surface volume. And then we know that the constant term is always 1. So if you see a polynomial and its constant term is not 1, we could automatically discard that as saying that's not an Ehrhart polynomial, okay? But we don't really know what happens in between maybe the constant term and the surface volume term, yeah? So one open question in this field, which is called Ehrhart theory, the study of enumerating lattice points in polytopes, is, well, can we give combinatorial interpretations for those coefficients? Okay. And in some particular cases we do, but it's actually really hard in general. Okay. Are there any questions so far? Feel free to interrupt me. Okay. And so what happens when we take a rational polytope, right? So maybe we have a polytope in the lattice, in the integer lattice, and kind of just maybe shift it by maybe a half translation or something like, which we can move it where the integer, the vertices are no longer lattice, okay? Well, actually Ehrhart's work is more general. It says that this counting function, L sub p, is actually a quasi-polynomial where the period divides q, and I'm taking q to be the least common multiple of the denominators of the coordinates of the vertices, okay? So that's a mouthful. But again, I can encode these Ehrhart quasi-polynomials in a generating series, and I get the Ehrhart series, or what we're calling the Ehrhart series, to be of this form. With now, this depends on our period, okay, which we didn't have before. And again, if q is equal to 1, we are in the lattice polytope case, okay? So maybe that wasn't very illustrative, and so I can say, okay, well, what is a quasi-polynomial? Well, quasi-polynomial is a function from Z to R of the following form, where now we have some periodic functions coming into play here, okay? Now you can still say, well, that's still not as helpful, Andres. And so an alternate definition of a quasi-polynomial is kind of, you want to think of this quasi-polynomial as having multiple parts, where we are now depending on the period Q, okay? And so we can think of this as multiple polynomials. And when we think about the Ehrhart theory of rational polytopes, so there's plenty of stuff going on in Ehrhart theory of lattice polytopes, and it's a very active area, but the Ehrhart theory of rational polytopes is less studied, and a lot of it is because you now start dealing with underlying subtleties coming from like number theoretic factors. As you can even see with this alternate definition of the quasi-polynomial, we have to think about this periodicity, okay? And so a special polytope that is in the title, I said, okay, well, it's fixed polytopes of the permutahedron, and this is the first time we now talk about the permutahedron. And so the n permutahedron is the polytope living in n space, whose vertices are the n factorial permutations of 1 through n, okay? And so here's some examples. If I just have 1, 2, well, there's only 2 permutations of 1 and 2, and so we only get the line segment. 1, 2, 3, we have 6, right? So 3 factorial is 6, and so we get this hexagon. And if we have 4, we get this truncated octahedron, okay? And so this is what we call the n permutahedron, okay? And so I want us to spend a little bit of time just saying, well, how can we describe this n permutahedron, okay? And so I told you that a polytope is a convex hull of finitely many points. Well, we have the description, right, that I gave you before. The permutahedron is the convex hull of all permutations of 1 through n, which ends up being the permutations of 1 through n end up being the vertices. But we can also describe a polytope through its inequalities, okay? And actually, you know, and when you're dealing with an inequality description of polytopes, you're really thinking about a linear system of equations. And if those linear systems have rational coefficients, you always get a rational polytope. And so kind of a point that I want to make is that when you're thinking about linear systems, there might be an underlying polytope. And when you have because linear systems appear everywhere in math, that means that maybe your mathematical problem can be reduced to an Ehrhart theoretic problem where you're just actually dealing with Ehrhart polynomials or Ehrhart quasi-polynomials, okay? But the inequality description for the permutahedron is you're summing up all entries up to n, and then we're taking all proper subsets of these things like that, and we're summing that where we have this inequality. And actually this equality, so if you notice before, you might have said, okay, well, we have a line segment living in 2 space, a hexagon living in 3 space, and a truncated octahedron living in 4 space. And so this equality is actually bringing down 1 dimension, okay? And so we have actually that the permutahedron is an n-1 dimensional polytope living in n space, okay? Again, I mentioned already the vertices, but here, what I really want to focus and what we're gonna really kind of use later on is this Minkowski sum description. It turns out that the permutahedron is the Minkowski sum of these line segments, or to translate actually, of these line segments, E, K, E, J, where you're taking J and K to be between 1 and n, okay? And I mentioned, yeah, as I mentioned before, the n permutahedron is n-1 dimensional, and every permutation of n is indeed a vertex, okay? And so I'm gonna spend a little bit more time talking about this Minkowski sum. And so here's my cheap sneaking into some graph theory. I was trying to upsell this a little bit. So if we're given a graph G with a node set n, we define a graphical zonotope to be the Minkowski sum of line segments EJ, EK for all edges JK of G, okay? And so if you think about the permutahedron, it is a graphical zonotope. And it's actually the graphical zonotope for the complete graph on n vertices, okay? And so maybe if you have some paper, you can try to play around with that and see to convince yourself that that's true, okay? And so graphical zonotopes, you could think about their Ehrhart theory also. And so there's really nice things coming actually from the Ehrhart theory of zonotopes, which I'll mention later. But I did want to mention that the permutahedron is a graphical zonotope. And so you'll see that later on, we should, because of this property that it's a graphical zonotope, we should be thinking about it having some graph theoretic notions in the Ehrhart theory. And that's for the standard permutahedron, the lattice permutahedron, we actually know what the Ehrhart polynomial is. And so the coefficient C sub k of the Ehrhart polynomial of the permutahedron equals the number of labeled forests on D nodes with k edges. Okay, and so let's do an example. For the hexagon has, actually, if we just look, let's come back to the picture just to see it. This hexagon is 2-dimensional, right? So let's imagine that we're just kind of just putting it on 2 dimensions. So if we're just caring about the affine span that it lives on, it's gonna be 2-dimensional. And so we have kind of like these, it's a triangular lattice in this case, right? Because we're cutting it by this hyperplane. So if we think about the Ehrhart theory, well, we can use Pick's theorem, right? So Pick's theorem says the number of lattice points is the area plus half of the boundary points plus 1, right? So what's the area of this hexagon? Well, how many lattice points are there actually? So there's 6 on the boundary and the interior, and that's it. There's just 1 in the interior, and that's it. So using Pick's theorem, we're kind of like, this parallelepiped has volume 1, this parallelepiped has volume 1, and this parallelepiped has volume 1. If I like take this middle point and I kind of just draw it by parallelograms, okay, break it into parallelograms. And so the area of this hexagon is actually 3. And what are the boundary points? Well, the boundary points are 6, so that half of 6 is 2. So the Ehrhart polynomial should be 3t squared plus 3t plus 1, okay? And that's what I wrote before, 3t squared plus 3t plus 1. But this theorem is claiming, well, each coefficient equals the number of labeled forests on, sorry, I should have said n nodes instead of d, on n nodes with k edges. And so the first one should be 3 nodes with 2 edges, 3 nodes with 1 edge, and 3, oh, it got chopped off, but with no edges. And so that's where we get the 3, 3, 1 in these coefficients. So I think that's pretty neat, right? But then you can also say, well, this first row is just the number of spanning trees, right? And this is what, Cayley's theorem, I think. And so that's n to the n minus 2. And so it turns out for the permutahedron, the leading coefficient is the volume, right? Or for any polynomial, Ehrhart polynomial, the leading coefficient is the volume. But for the permutahedron, we know what that volume is, and it should be n to the n minus 2. Okay? Everybody with me so far? Are there any questions? Nope. Okay. I'm gonna assume that we're okay. And so here maybe is now to please the algebraically inclined people. And so now we're gonna think about a group action. So we're gonna take an action. So we're gonna consider the permutahedron under the action of the symmetric group, okay? So what are we gonna do? We're gonna take a permutation and act on the number of points in the permutahedron, okay? And so that's what we're, in my title, I said, the title was Fixed Polytopes of the Permutahedron. And so now this is where we've already talked about the permutahedron. So now let's talk about the fixed polytope business. So the fixed polytope of the permutahedron under a permutation sigma of n is all points in the permutahedron that are fixed by that action, okay? Nothing too crazy. And so in general, Alan Stapledon in 2011 said that something like that for any polytope, if you act on it with an element of a group, you're gonna get that it's actually a rational polytope, okay? And so that's where the rational polytope business comes into play, because now our fixed polytopes are not always going to be integral, okay? But maybe we need to convince ourselves or understand this a little bit further through an example, okay? So let's just look at the fixed polytopes of pi 3, right? Of the 3 permutahedron, which is just the hexagon that we talked about before. So we're going to act on it by the transposition 1, 2. So what does that do? Well, it transposes the first and second entries of all points, right? But here I'm kind of detailing the vertices, right? But I said, okay, well, the fixed polytope is all points that are fixed. So what are the points that are fixed here, right? Well, 1, 2 induces a reflection. And it's actually this reflection on this hyperplane, right? And it turns out that this blue line segment here, and I'm sorry if you can't see some of my colors, I should have been more mindful of that, but I hopefully by me kind of pinpointing, you'll see what I'm talking about. This polytope here, this line segment, is the fixed polytope in this case, okay? So the reflection is on the hyperplane x1 is equal to x2. And so the fixed polytope, pi 3, 1, 2, is a one-dimensional rational polytope. So in this case, it's this line segment. And well, what are its vertices? Well, its vertices are, I shouldn't do arithmetic on hand, but it's 3 halves, 3 halves, 3, right? And then here also 3 halves, 3 halves, 1. So those are the vertices. And it contains this interior point, okay? But I said, okay, well, in Ehrhart theory, we care about the dilations of the polytope. So let's dilate the polytope, okay, by integral values. So boom, here it goes. And so if you didn't understand the definition of an Ehrhart quasi-polynomial a few slides back, well, hopefully this example kind of gives you an idea of what it's doing, right? It turns out that in this case, we talked about the period, right? Or the denominator, the period dividing the denominator of the, sorry, the period, the denominator of the polytope being Q, right? And so the period divides Q. In this case, Q is the LCM of all vertex denominators. And so I said that these points were 3 halves, 3 halves, 3, and 3 halves, 3 halves, 1. Well, what's the LCM of the denominators? It's 2. So our period is 2. And in this case, we only care about when the dilation is even or the dilation is odd, right? Because since it's a half integral, when we dilate it by an even number, we're back to a lattice case, okay? And so again, here we have the Ehrhart quasi-polynomial. So it's t plus 1 and then t, right? So t plus 1 if t is even and t if t is odd, okay? And so what, again, the Ehrhart quasi-polynomial is enumerating the lattice points. And so in this case, if t is just 1, how many lattice points do we get? Well, we only get 1, right? And so if t is equal to 1, we get that the lattice point enumerator is just 1. If we dilate it by a value of 2, we get that it's integral again. And how many lattice points do we have? Well, we have 1, 2, and 3 in the second dilation. And so t is equal to 2. 2 plus 1 is 3. Okay? Everybody with me? Okay, great. And so some other examples of some fixed polytopes. Now let's just look at what happens in the case for the 4 permutahedron, right? Again, this is the truncated octahedron. And here, if I'm acting by the permutation 1, 2, 3, what I get fixed, and it's maybe hard to see, but this point is on this hexagonal face over here, and this point here is on a hexagonal face over here. So you get this line segment cutting through the interior of this 4 permutahedron, okay? And that's when I'm acting on it by 1, 2, 3. But what happens when I act on it by just 1, 2? Well, it actually cuts, again, 1, 2 induces a reflection on x1 is equal to x2. So it's cutting it by 1 hyperplane, kind of just slicing the permutahedron in half. Actually, I have a little permutahedron here. And so it's just like cutting it straight down. And so you can see this yellow permutahedron, okay? And so when we cut this thing, well, what's our fixed polytope? It's actually this hexagon. And now if you're an observant person, you can see that this is a line segment and this is a hexagon. And so does that always happen? And so for the 4 permutahedron, all fixed polytopes can either be a point, a line segment, or a hexagon. Now the question is that true for any permutahedron? Do we get something that mimics this like permutahedral values, yeah? And so it turns out yes. And so this is our theorem. We're able to describe I described to you what the standard permutahedron looks like. And here we're describing what the fixed polytopes look like, okay? So here are 4 different ways to describe the permutahedron. Again, this is just following, the first one is following Stapledon's description, right? It's all the points that are fixed by the action sigma. But then we have, again, our inequality description, right? Where this mimics the same permutahedron, the same equality and inequality of the standard permutahedron, which makes sense, right? Because these fixed polytopes live inside the permutahedron, right? But what's neat is now that we're having the cycle play a role. And so if for any I and j, which are in the same cycle of our permutation sigma, then we get xi is equal to xj, right? And so we have those things cutting into the polytope. So we're now restricting ourselves multiple times. And so it's the convex hull of m factorial points, where if I write the permutation with m cycles, okay? Again, this might mean nothing, it's just mathematical jargon. So let's try to do that an example to kind of illustrate this a little bit more, okay? But the last thing is that it ends up that these fixed polytopes are also Minkowski sums, and we really use this later on, this description of this Minkowski sum, right? But from this last like kind of translation or this shift here, this tells us that it's half integral. And so that means that what we're going to head towards is trying to give an Ehrhart quasi-polynomial for these polytopes. But that's nice in a sense because now we only care when it's even or when it's odd, okay? But these fixed polytopes turn out to be zonotopes that are combinatorially isomorphic, meaning they have the same phase structure as the permutahedron. Okay? And so this theorem that I just showed you provides a vertex description for these fixed polytopes as a refinement of Stapledon's description. Okay, so here we have our friend that I showed you earlier, this fixed polytope of the permutahedron when it's fixed by the transposition 1, 2. Okay, so here's the description. Well, what are all the points that are fixed? Well, it's actually all the vertices, but then you also, but not all of them are vertices, right? You get this point also being fixed, okay? But what our theorem says is, well, it's now enough to consider the vertices with consecutive order increasing in integer positions 1 and 2. So when we're looking here, this tells us, okay, well, we can just look at 1 and 2. So the number of such vertices is the number of orderings of 1, 2, and 3, and 4, right? And there's 3 factorial, which is equal to 6. So we know what the dimension, the number of vertices is. Okay. Are there any questions so far? I might be going a little too fast. No questions? Okay, great. And so, well, I showed you the Ehrhart polynomial for the standard permutahedron, right? And we figured out what its volume was. The volume is n to the n minus 2. And so our theorem now gives a volume for these fixed polytopes, okay? So if sigma is a permutation of n whose cycles have lengths L1 through Lm, then the normalized volume of the subpolytope or this fixed polytope is n to the m minus 2 times the GCD of these lengths. And so I don't know about you, but I think this is very nice because it's somewhat simple, yeah? It's like a nice closed form. And this generalizes the theorem for that. And so the theorem that the volume of the permutahedron is n to the n minus 2 is due to Richard Stanley. And so this generalizes Richard Stanley's theorem, right? If we take m to be the full cycle, and where it's just n, we recover this again, yeah. Oh, yeah, and so when we act on by the identity, I forgot I put this in. So when we act on the identity, we recover Richard Stanley's result, okay? Awesome, are there any questions? No questions? Awesome, okay. And so here we have the same picture, but now I've kind of drawn it so that you can see all the lattice points. And so we see all the lattice points of the permutahedron, and we see that the fixed polytope has some lattice points in it, right? And so we want to enumerate those lattice points. And so if it wasn't clear before, we can write again, we're acting by the transposition 1, 2, right? Which is an element of S4. And so we can write this fixed polytope, the blue one, as this Minkowski sum, okay? And so what's gonna come next is that we're gonna aim to enumerate the lattice points of those fixed polytopes, okay? So first, let me tell you a little bit about the Ehrhart theory of lattice zonotopes. So zonotopes, as we've discussed before, can be tiled by half-open parallelotopes, okay? In 2 dimensions, there are parallelograms and then parallelepipeds, general parallelotopes, okay? And this is a result of Shepard from 1974, okay? And so here we have our friendly 2-dimensional 3 permutahedron, right? And it can be tiled by half-open parallelotopes. So here we have, this is half-open, meaning that some of the boundaries are not included, yeah? And so here I tiled it by half-open parallelotopes. And so Stanley, Richard Stanley in 91 gave us a formula for the Ehrhart polynomial of a zonotope. And so, if we take Z to be a zonotope generated by integer vectors U, where U is the set of U1 through UK, then the Ehrhart polynomial of that zonotope is the sum of all subsets of U, where we take the volume of the parallelotopes generated by those subsets, okay? And so essentially what we're doing is we're figuring out, well, what's the Ehrhart polynomial? Well, it's enumerating kind of giving us the volume for each of these half-open parallelotopes, okay? But the question is, well, what if I have a rational translate of a lattice polytope? And so here, this is actually the fixed polytope pi 4 fixed by 1, the transposition 1, 2, okay? Well, we see that it no longer has lattice vertices, right? But they're still lattice points, right? And so if we decompose it, we can still decompose it into half-open parallelotopes, but now some of those parallelotopes no longer contain lattice points. For example, oh, well, this one doesn't contain one, and this darkened point is actually supposed to be this vertex, which is not a lattice point, which I didn't color purple, okay? Right? And so, again, we're gonna let sigma be an element of the symmetric group, and we're gonna let it have cycle type lambda, where lambda is the length of these, if we write it as like the cycle decompositions, the length of those parts. And so it turns out that the zonotope, so the fixed polytopes is the zonotope of these particular vectors, okay? And so here's maybe another, we said, okay, well, if the standard permutahedron had some graph theoretic notions in the background, well, then the fixed polytope should also, right? And so it turns out that these, the linearly independent subsets of this set are in bijection with forests on the vertex set M. So for the standard permutahedron, it was on the vertex at N, but now we really just care about the vertex at M coming from the lengths of these cycles, okay? And so we're gonna group the forests by the underlying set partition of M. And so the nice part is, like, now we don't really even care about the geometry in a sense. We're kind of just looking at set partitions of M. And if we think about it graph theoretically, just like as grouping the forests, okay? And so if all the lengths are odd, then the fixed polytope is integral. And so we kind of just use Richard Stanley's formula to give us the lattice point enumeration for the fixed polytopes. And so this V sub pi is the sum of the volumes of these parallelotopes coming from the decompositions before. But those things are actually the volumes, sorry, the V sub is the sum of the volumes for all forests given rise to the partition. Okay. And so if some of the L sub I are even, then we have to worry about the rational stuff, because now these fixed polytopes are half integral. So the question is, which forests correspond to the half open parallelotopes containing lattice points, okay? And so here's our setup again. And so a set partition of M is lambda compatible if for all blocks in the partition, one of the following conditions hold. Either one of the L sub j is odd for some j in the blocks, or the minimum 2 valuation among all L sub j is attained at least twice. So this is a mouthful because, well, one question is, what's a minimum 2 valuation, right? And so here, the 2 valuation of a positive integer is the largest power of 2 dividing that integer. So for example, what's the 2 valuation of 24? It's 3, okay? So if we're looking at, so now we don't really even care about the geometry. Now we're just really looking at what happens when we're partitioning our vertex set, okay? And so if one of the lengths of those L sub j is odd, then we say it's lambda compatible. Or if we have that the set of L sub j, the minimum two valuation of the number of those L sub j is attained at least twice, okay? And so one lemma is that the half open parallelotope contains the volume many lattice points if the underlying set of F is lambda compatible. Otherwise, if we have these half open parallelotopes and they're not lambda compatible, then they contain no lattice points, okay? And so this is kind of an ugly formula. It's just like on your face, but we were able to give the Ehrhart quasi-polynomial in general, okay? And so we really care about just the set partition of the vertex set, right? And so in the proofs of these things, we kind of do rely a little bit on some graph theory, but in general, we're just really caring about the size of these cycles, right? And I think that so we write v sub pi to be this sum, right? But yeah, this Ehrhart quasi-polynomial is the lattice point enumerator for these fixed polytopes. And if, again, I told you, okay, well, we care about generating these or putting these Ehrhart polynomials or Ehrhart quasi-polynomials in generating series. And so when we do that, we get this Ehrhart series. Again, I didn't write it in the form that I presented to you before, but now again, we're splitting these two cases into the case where lambda is, the set partition is lambda compatible and the set partition is not lambda compatible. And we have some Eulerian polynomials popping up in the numerators, yeah? And so I think that's where I want to stop. Yeah, so thank you.
Let's thank Andrés.
Awesome, thank you. Are there any questions?
Questions?
I know I went through some of this kind of fast, but.
I have a question. So
yeah.
You have these theorems that you proved. What methods or tools do you use to prove them?
Yeah, so we really did rely on the number theory of these things, and so so we use some number theoretic things, and it's not advanced number theory. It's really just like basic number theory. But we also use some graph theoretic things, and that really just comes from the idea that we're bijecting here. These linearly independent subsets are in bijection with the forests of the vertex set. And so for some of these things to figure out the volume, we needed to choose kind of a graph where we can think about kind of grouping the vertices. And so in the paper, I think we might have used the claw graph. And so, yeah, I guess I won't say anything more than that, but.
Did you have a choice and you chose the claw graph, or that was natural for certain reasons?
It was natural because of the matrix, of the adjacency matrix that we got. But really, I think we could have used any graph that made sense. But I think for us, it was like very obvious that the claw graph was probably the best. And I think, again, if I showed you the matrix, you would see that it made kind of sense. Yeah.
So I have a question.
Yeah.
Can you relate this to the Bruja order on the symmetric group? So gradually generating words by transpositions, and then the sort of building theory for that.
Yeah.
Can you formulate your results in that building theory, and then possibly extend it to polytopes corresponding to other groups?
Yeah. The short answer is I don't know.
Okay.
But I think, and I'm not sure about the Bruja order, but I will say that in kind of in the spirit of your question, if we think about subgroups of the symmetric group, we can play the same game, and it turns out that it's not much different for at least subgroups of the symmetric group. But yeah, I wouldn't know that.
So sorry, you're saying about the polytope fixed by all the elements of a subgroup.
That's right. Yeah.
Yeah.
That's right. Yeah. And so the story is very similar.
Yeah, so I guess then by Cayley's theorem, you're starting to access other groups as well.
Yeah, and so I haven't actually explored many other groups. I mean, it's very natural because of the symmetry of the permutahedron to use the symmetric group, but yeah, we could explore the Ehrhart, the equivariant. So this is called equivariant Ehrhart theory. So equivariant, for, obvious reasons that we're using group actions. But yeah, I haven't explored other groups, but that would probably be a nice natural direction. And I think for me, the next natural direction is, well, we saw that these things are coming up as graphic zonotopes. And so this, if you know about Coxeter groups and things like this, this is all from root systems of type A, but you could ask the same thing about, well, what about the permutahedron arising from other root systems, type B, C.
Yeah, orthogonal groups and such like,
And so I haven't explored those, but I think that that's something that I would like to work on.
Great, well, thanks, very nice talk.
Thank you.
More questions?
More questions. I must have been very clear or very non-clear.
Yeah, it was very nice. You had a lot of examples. They were very helpful for me.
Awesome. Yeah. And so I maybe should have actually posted, where is that picture? I should have done the example for this one, right? But you can kind of see what the Ehrhart polynomial, because this is a two-dimensional thing, so we're only going to have two cases, right? And so what would we have? Well, we would have, again, we're counting the lattice points in two-dimensional things, and two-dimensional, one-dimensional, zero-dimensional. So in the odd case, we would get 3. So here we have the two-dimensional one. So 1, 2, 3, 4. Sorry, I'm getting confused. Can you still see my screen?
Yes.
Okay, awesome. Yeah, so we should have how many here? 1, 2, 3, 4. So it should be 4t squared plus 2t plus nothing, right? Because there's nothing on the other ones. I think that's right. Should have prepared this instead of doing it off the top of my head, but yeah, we should be able to see the lattice point and numerator just from the volume of these things. Yeah, I think that's right. At least for the odd case where things in odd dilation. Right, because if it was an even dilation, then we would go back and just dilate it by an even factor, and we would have actually lattice points in the vertices again, right? Because this is half integral. Yeah. But any other questions? If not, I want to actually just take 2 seconds of your time. And so I'm going to stop sharing this screen. And I wanted to advertise something real quick. Well, three things. One is next summer, the Fields Institute is hosting a queer and trans combinatorics conference. So if that's interest to you, you can look it up at the Fields Institute. And actually, let me type the website. It says queer trans math, but now it really is a combinatorics conference. And it's hosted by the Fields Institute.
It's there in the chat.
It's in the chat, yeah.
Thank you. If they let us go to Canada.
Yeah, if they let us go, yeah. It might actually end up turning virtual, so we'll see. But another thing I wanted to show you all, and I'm trying to pull up the slides real quick. Here we go. I'm going to share the screen again. So as some of you may know, it is Hispanic Heritage Month, Latinx Heritage Month in the United States. And so from September 15th to October 15th in the US, we celebrate Latinx Heritage Month or Hispanic Heritage Month. And I wanted to promote Lattisms. Lattisms.org is a website that aims to give visibility to Latinx mathematicians and their work. And so every day since September 15th up to October 15th, if you go and you click View Today's Mathematician, we feature a different mathematician every day. And this is the 5th year that it's running. And so we're in our 5th year anniversary. And in that spirit, we're actually, hopefully by the end of, or by May of next year, hopefully, we'll have a book out called Testimonial Stories of Latinx and Hispanic Mathematicians, where we're featuring about 27 different mathematicians, and there are some combinatorialists in there. And you know, the website kind of details their more professional story, and the book that we're writing will get really down to the stories of how they got into mathematics and more of their personal stories related to that. And so I wanted to advertise that and put that out there if that interests you. Yeah. But yeah, that's all I have to say.
Thank you.
So, thank you. Let's say Andrés again.
Awesome. Thank you all so much for coming and allowing me to speak.
It was a pleasure to have you.
Thank you. Take care, everybody.